me. And hi, everyone. I'm Jamie Caldwell. I'm a postdoc at the University of Hawaii at Manoa, although I'm physically based at James Cook University in Townsville, Australia right now. And as Megan said, we're really excited to share a demonstration of this multi-factor coral disease forecast. And this project has been a collaborative piece of work through the University of Hawaii at Manoa and NOAA Coral Reef Watch. And it's primarily been funded by NASA's ecological forecasting program.
If there are any technical difficulties that you have as we go, we'll keep the chat open to handle any of those. And then please put your questions as we get, that you may have throughout the presentation into the Q&A. Thanks. Go ahead, Jamie.
Thanks. So as I'm sure most of you are aware, coral disease impacts are pretty widespread throughout the world. And this is just an image illustrating that multiple disease has been reported in pretty much every coral reef region around the globe. And the impacts are quite variable. Of course, some areas are hit much worse, like Florida and the Caribbean, whereas others seem to have lower disease levels. And importantly, I think for disease and somewhat contrasting some of the issues around coral bleaching is that several of the hypothesized factors to drive disease are really associated with some local impacts. So potentially things that managers or scientists can study and do something about in terms of preventing disease in the future. So we think there's potential here for a lot of different research. But early warning systems, which can really help aid these responses, are currently quite limited in scope. So as far as we're aware, there's only one early warning system that's currently moving forward in near real time, and that's as part of Coral Reef Watch's product suite, which is this experimental coral disease outbreak risk product that I'm showing here. And if you're not familiar, this product was released, I think, back in 2011. And its models based on a couple of different temperature metrics. It's specifically for the Great Barrier Reef in Australia and Hawaii. And it only produces forecasts for acropora white syndromes. So some of the impetus behind this project is that we are hoping to expand the system to hopefully make it more useful to different coral reef researchers and managers. So the overall project goals here were first to create finer resolution predictions. So the product that I just showed was originally 50-kilometer resolution predictions, which is both useful and not useful at the same time, I would say. And so I'm really pleased that Scott led this work, and these predictions are now at about 5-kilometer resolution, which I think is much more useful. We have also looked at a number of different coral disease types to expand this product to, and are currently predicting for both white syndromes in family Acroporidae and also growth anomalies in more massive corals like Porites. We're also expanding the regions that these disease forecasts are available for, so across the Pacific Ocean. And I think a really exciting aspect of this new product is that we've been developing these interactive forecasts and scenario tools so that users can interact with the data more closely and refine predictions and hopefully see the data that is really most useful to them. Now, before I jump into the tool itself, which will be the focus of most of this demonstration, since I know there's a lot of researchers in the audience, we wanted to first just talk a little bit about the models themselves so you have an idea of what's under the hood before we look into the forecasts themselves. So what we've been using is fairly simple regression models in a Bayesian framework. And what this means is that we're relating a suite of ecological driver variables to disease risk to predict disease risk in different locations and times in the future. So as an example of what one of these relationships looks like, here on the x-axis, we have coastal development going from low to high and disease prevalence on the y-axis. And what this model would show us is that we'd expect disease prevalence to increase as coastal development increases. Another important facet of this is that we also have this uncertainty in the shaded gray. And so we also see that the uncertainty in these predictions increases in locations that are closer to coasts that are more developed. So in the models, what we've done is compare disease risk with a suite of different benthic characteristics like colony size and coral cover, coastal development, as I've just shown, different wave energy metrics, different thermal stress metrics, so sea surface temperature, and metrics associated with both cold and hot thermal stress, fish community, and several water quality metrics, trying to capture both chronic and acute water quality changes through time. And we've developed slightly different models for the different disease types and for the different regions. And we'll be happy to talk about those more at the end, but this is about the level of detail we think is sufficient for you to understand the tool that we're about to show. Now, just to give an idea of what predictions mean in this modeling framework, here is a toy example of what these forecasts that we'll be showing you in a moment represent. So on this plot, we have time on the x-axis and disease risk on the y. And to the left of this vertical dashed line is what we're calling nowcast. And essentially, this dark orange line is our median model prediction. And the orange around it, the shading, is our uncertainty in that prediction. And that's based on our uncertainty in the disease model itself, because of course, we're not exactly sure how each environmental covariate relates exactly to disease risk. And these nowcasts are using actual observations or measured variables, for instance, through satellite observations. And this differs from our forecasts, which are actually forecasts of some of these variables that can change through time. So some of these predictor variables that I showed a moment ago are relatively static. They don't change very quickly and often stay the same, but some actually change through time, such as temperature and water quality. And so these forecasted climatological variables are then incorporated into our models to make disease forecasts in the future. So the most important thing to take away from here is that there's a lot more shaded area of uncertainty in the forecast. And that's because it accounts for both the uncertainty in our model itself, as well as the uncertainty in these predicted observations. So of course, we're less certain about what the temperature will be in 1 or 2 months in the future compared to what it was 1 week ago when we were able to measure it. So these models were built using data from all these locations here in the Pacific Ocean. And this is on the tool for you to explore. And probably a lot of people in this webinar have actually contributed to these disease surveys, so we really appreciate it. Some of these disease observations were also collected within the auspice of this project itself. And you can zoom into any of these locations to see where they are, the number of surveys, and who collected them, and what year those surveys were collected. So that's really the basis of the models themselves. And I've zoomed into Maui here because we'll be focusing on that as somewhat of a case study for this demonstration. So West Maui is considered a priority watershed. It's shown here. It's quite a beautiful area within Hawaii. And it usually looks like this, but it's a priority watershed because sometimes it looks like this. I'm sure a lot of you are familiar with reef regions that are quite dynamic and have issues such as water quality problems like this. And so we focused here just because we think this is a good example of how to use this tool. But of course, wherever you work within the Pacific Ocean, we hope this is useful. So West Maui is within the island of Maui within Hawaii, which is pictured here. It was designated a priority watershed by NOAA, but I believe it was done so in talks with multiple different stakeholders and managers and scientists. Overall, the region has about 30% coral cover, which is quite a bit lower than historical estimates. There's fairly low disease prevalence, about 6%. Herbivorous fish biomass, about 9 grams per meter squared. And turbidity is not too bad. So we have a measure of light attenuation, which is 0.05 per meter. So how quickly light attenuates through the water column. Now, these are the mean estimates across this whole region, but what's really interesting is that the coral reefs here are really variable. So I normally really dislike when people put small tables on PowerPoint presentations. So I hope you'll forgive me because I still think this one's useful, primarily because of the colors. So what this is showing here, this is a table from data collected primarily from the Nature Conservancy within this priority watershed. And it's ranking reef resilience across the different sites, looking at different measurements and quality of the different reefs, such as coral cover and diversity and coral recruitment. And anywhere that's green is showing low values or good. And as you get to warmer colors, you get high values and bad. And so it's really interesting here, if you look across a row, which is a single site, not all these measurements are really good or really bad. It's quite variable within sites. And if you look a long column, so for instance, the first column of coral cover, it varies quite substantially to, less than 3%, I believe, up to 64% coral cover. So in a small region, quite variable differences in the coral reef community. So this is just a little background information to keep in mind as we go through the tool in a moment. So the new experimental product will look something like this. This is a mock-up page for the Coral Reef Watch website. And it'll show the overall Pacific Ocean where this tool is available for. And in each of these boxes is a smaller virtual station that users can click on. And then it'll take you to a page that looks something like this. We're hoping this is familiar to most people in the audience. It replicates very similarly the coral bleaching forecasts. And we've done that with the hope that this will make this product really easy and a natural transition for people to use who already use the coral bleaching products. And in most ways, it'll look fairly similar. We'll have a map of the region that you've clicked on, and then you can see 4, 8, and 12-week forecasts of coral disease risk with some gauge of that measurement. What's new and unique to this product, however, is the shiny explorer that we're embedding within the website. And so I'll show you some videos of what that will look like now. So this is the main forecast page. And when you click on it, you'll see a map with each pixel colored by its disease risk. It's looking quite bland here, which is actually a good thing. It means we're predicting very low disease risk. If we move into Maui here, right in our priority watershed, you can click on a 5-kilometer pixel and then scroll down to see the predictions for that specific location for growth anomalies and white syndromes. You can click on and off the confidence intervals. You can also toggle between the satellite view to zoom closer in and make sure you're actually looking where you're interested in, for instance, where you might have some monitoring sites, and then toggle back to the 5-kilometer forecast to make sure you're looking at the pixel of interest. We're also incorporating different management areas, so marine reserves, and you can similarly click on those areas if you want an overview of the forecast for a larger region that encompasses multiple 5-kilometer pixels. Again, disease risk is really low in these areas, about 2 to 4%, and it's not changing too much through time. So it mostly looks like straight lines, but I think that's something we like to see. We don't want to see really high levels of disease risk predicted. Next, we have our scenarios page. And the idea behind this page is to allow users to both refine the predictions from the 5-kilometer pixel, because we know that if you're actually looking to go out and do a monitoring effort or an intervention, that 5 kilometers is actually a big area of reef. And we understand that reefs vary even in small distances. So we're hoping this will allow users to actually refine the predictions if you know specific aspects or elements of your coral reef, or if you're interested in planning some intervention. So the scenarios page looks pretty similar in terms of the map, and you can click on the 5-kilometer pixels. So here within this watershed, I just want you to notice that, as expected based on the table I showed earlier, the baseline disease risk is quite variable in this region. So for instance, right here, the baseline disease risk is considered 9%. Now in this scenario, we're allowing users to move some of these sliders to adjust the values for water quality, which incorporates chlorophyll A, and turbidity, herbivorous fish abundance, and coral cover and size. So for instance, if you knew this location actually had worse water quality than the average in that region, you might expect disease risk to be a little bit higher. But we also know that the herbivorous fish is quite a bit lower in that site. And we know that coral cover is much lower than 90%. It's closer to about 30%. So now that we've refined to the prediction to the specific area, we actually predict that disease risk to be just 5% rather than 9%. Now, another way to use this is to consider different interventions. So let's say at the same site, the goal is to improve water quality 20% above the average of the area. In that case, disease risk would be reduced by about 10%. So it dropped all the way to 1%, and any higher, I believe it'll go down to 0. And since one of the reasons this is a priority watershed is to improve water quality, this shows that between 20 to 40% improvement. So you can see the actual numbers for chlorophyll A and turbidity reductions here should actually reduce disease risk all the way down to 0. Finally, we have an about page, which gives you a bit more information about the tool itself. So we have some photographs of what growth anomalies and tissue loss looks like on different species of coral, some descriptions of those diseases, information about our funding sources, and publications to support this research, all with hyperlinks where you can get more information. Of course, we also have presentations and a number of other outreach information that we can provide if there's interest, but we have the key elements we hope within this about page. Now, finally, even though I'm presenting this myself, this is on behalf of a really wonderful collaborative working team. So everybody who is pictured here has been part of this project and helping. In addition to all these people, we've had a number of funders and partners who have helped collect data, given really useful information or inference about different aspects of this project or modeling or response. And we're really appreciative of all that. And finally, before I open it up to discussion and question and answers, I want to preempt that this isn't available yet, but it will be by the end of the year. If you registered for this webinar, we have your email, and we'll send you an email when the tool is available. If you logged in directly from ICRS and haven't registered, you can follow this hyperlink here, and I can put it in the chat box in a moment. And if you register for this event, then I'll have your email to send out when the tool is available.